Hello, motion curves. In this lecture, we'll study if one of these three curves is given, then how to draw other two curves: acceleration time diagram, velocity time diagram, and position time diagram. Now, before we start drawing these curves, you must know all these points. Pause the video and note down these points. Acceleration is slope of Vt diagram. Nothing new here. When velocity is function of time t, dv by dt is acceleration. In mathematics you have studied, if equation of a curve is y is equal to fx, then slope of the curve is dy by dx. So it's same thing here. When velocity is function of time t, then dv by dt slope of the Vt diagram. And what after all dv by dt? It is acceleration. So acceleration is dv by dt. This is the expression we have interpreted in this manner. Acceleration is a slope of Vt diagram. Similarly, velocity is slope of xt diagram. So v is equal to dx by dt. Area under Vt diagram from t equal to t1 to t equal to t2. It is change in position, and change in position is nothing but displacement. Area under Vt diagram from t equal to t1 to t equal to t2 gives you displacement in this time interval. Area under At diagram, acceleration time diagram, in a time interval, so say t1 to t2. Area under At diagram from t equal to t1 to t equal to t2 gives you change in velocity. So now remember these last two statements in this manner. Area under Vt diagram gives change in position. Area under At diagram gives change in velocity. And this fifth point is very important. That is, you will have to take some efforts to remember this. Check here. Moment of area under At diagram from t equal to t1 to t equal to t2. What is that moment of area? While solving problems, you will understand it better. Right now, try to remember it. Moment of area under At diagram from t1 to t2 about t equal to t2 plus initial velocity. This is initial velocity, means velocity at t equal to t1. It is initial velocity in this time interval. So initial velocity into t2 minus t1, that is the duration. It gives you change in position or displacement. This is very important statement in the sense it gives you, or this formula gives you directly position or displacement. It gives you directly position or displacement from At diagram. Now a very important thing. If I ask you how Vt diagram is related with acceleration, Vt diagram and acceleration, how Vt diagram is related with acceleration, then you should answer me, slope of Vt diagram is acceleration. Okay. But other way around, if I ask you how At diagram is related with velocity, how At diagram is related with velocity, then you should answer me, area under At diagram gives change in velocity. So Vt diagram and acceleration, At diagram and velocity. How Vt diagram is related with acceleration? Acceleration is slope of Vt diagram. And how At diagram is related with velocity? Area under At diagram is change in velocity. Similarly, if I ask you how velocity is related with xt diagram, velocity and xt diagram, listen to the statement very carefully. How velocity is related with xt diagram? You should say velocity is slope of xt diagram. But other way around, if I ask you how velocity diagram, Vt diagram is related with position, then you should say area under Vt diagram gives change in position. read this problem. A particle starts at origin with no initial velocity and moves along a straight path with the acceleration varying as shown in figure. Draw velocity time diagram and position time diagram for the duration. What is that duration? T equal to 0 to t equal to 40. In this duration, you are asked to draw Vt and Xt diagram, position time diagram, that is Xt diagram. Information we have is at t equal to 0, V is equal to 0 and X is equal to 0. Now watch the diagram very carefully. If you remember in earlier lecture on motion curves, we considered only the motion in which acceleration was uniform, that is velocity increasing uniformly, velocity decreasing uniformly, or velocity constant, that is acceleration 0. But this is the problem in which acceleration is varying. From t equal to 0 to t equal to 10 seconds, acceleration is increasing uniformly. So it is variable acceleration. From 10 to 20 seconds, acceleration is constant 0.8. So from t equal to 10 to t equal to 20, it is same particle but moves with uniform acceleration. Then at t equal to 20 seconds, acceleration instantly drops to 0.25 meters per second square. And after that, acceleration goes on reducing uniformly. So again it is variable acceleration motion. So here acceleration is reducing. Don't say that it is retarded or decelerated motion. Many students, they get confused with this. Remember, here this is not velocity reducing, it is acceleration reducing. But from t equal to 20 to t equal to 35 seconds, check carefully, y coordinates of this graph positive only. That means throughout the motion, throughout this interval, acceleration is positive. That means velocity is increasing. 20 to 35, velocity is increasing. Remember, acceleration is positive. This is AT diagram and not VT diagram. So don't get confused. Throughout the motion, watch here, y coordinate in the sense acceleration is positive. So up to t equal to 35 seconds, velocity goes on increasing because it is positive acceleration. 35 to 40 seconds, velocity remains constant. Nowhere velocity reduces. So it is not decelerated motion at all. It's very mechanical to draw Vt and Xt diagram. Just remember those 5 points I have given you earlier. So to draw Vt diagram, you should find values of velocity at t equal to 0, t equal to 10, t equal to 20, t equal to 35 and t equal to 40 seconds. So at these important instants, you should know velocities. You will be able to draw Vt diagram. What is importance of these instants? Try to understand. 0 to 10 seconds. In this interval, it is variable acceleration motion. 10 to 20, it is uniform acceleration motion. From t equal to 20 to t equal to 35 seconds, it is again variable acceleration motion. Here acceleration is reducing. And 35 to 40 seconds, here acceleration is 0 in the sense it is uniform velocity motion. So in these 4 intervals, 0 to 10, 10 to 20, 20 to 35 and 35 to 40. In these 4 time intervals, it is the same particle but its motion is governed by different equations of motion. So at each of these time instants, equation of motion changes, and that is why we say these are important instants. So at all these instants, you should find velocity values. It's very simple. AT diagram is given, and that is why I am asking you this question. How AT diagram is related with velocity? Area under AT diagram gives change in velocity. Exactly this information we are going to use. So area under AT graph from t equal to t1 to t equal to t2 gives change in velocity. Now select intervals carefully. Time intervals. The time at which velocity is known and time at which velocity to be found out. This is how we use AT diagram to find velocity at any given particular instance. Now at t equal to 0, velocity is 0. So this is the instant at which we know velocity at t equal to 0 to v equal to 0. And we want to know velocity at t equal to 10. So select the interval t equal to 0 to t equal to 10 seconds. Now in this interval, area under AT graph. Area under AT graph. So this area, it is triangular area, base 10, height 0.8. So 10 into 0.8 by 2. So this is area under AT graph from 0 to 10 seconds. Now t1 is 0 and t2 is 10 seconds. This gives you velocity at t equal to 10 seconds minus velocity at t equal to 0. Now velocity at t equal to 0 is known. At t equal to 0, velocity is 0. So put it here and you have found out velocity at t equal to 10 seconds as 4 meters per second. Now continue. Next interval from t equal to 10 to t equal to 20 seconds. Now here, since you must know all details, remember to find velocity at t equal to 20. Right now our aim is to get velocities at all important instants. So to find velocity at t equal to 20 seconds, choose interval, the time at which velocity is known and time at which velocity to be found out in this manner. So can you choose interval 0 to 20 because velocity at t equal to 0 is known and we want to know velocity at t equal to 20. So can we choose a time duration 0 to 20? Yes, absolutely correct. But it's better to choose velocity at t equal to 10 seconds now because velocity at t equal to 10 seconds is also known. Time at which velocity known and time at which velocity to be found out. 10 to 20 it will be smaller area you will get and shorter expression you will get here. So it's better to choose a t equal to 10 seconds. Now if AT diagram is given and you want to know velocity at t equal to 15 seconds, you can consider 0 to 15 seconds. You can consider 0 to 15 and find that velocity. Okay. So now consider duration t equal to 10 seconds to t equal to 20 seconds. In this duration, what is area under AT diagram? So it is rectangular area. Base is 10 from 10 to 20. So it is 20 minus 10, that is the base, and height is 0.8. So 10 into 0.8, that is equal to final velocity in this interval final, that is velocity at t equal to 20 minus velocity at t equal to 10 seconds. So we are using this formula only to find velocity at important instants. So put t equal to 10 seconds, velocity as 4 meters per second and you will get the answer. So velocity at t equal to 20 seconds is 12 meters per second. Now next interval will select 20 to 35 from t equal to 20 seconds to t equal to 35 seconds. Now in this interval, what is that area? So area under AT diagram is triangular area. What is base of the triangle? 15. From 20 to 35, that is 15 seconds. That is base. And what is height? 0.25. So base into height by 2, that is that area under AT graph. So base 15, height 0.25 divided by 2. So area under AT graph is change in velocity. So v at t equal to t2, that is 35 seconds, and v at t equal to t1, that is 20 seconds. Now put velocity at t equal to 20 seconds in this equation and you have found out velocity at t equal to 35 seconds. Okay. Now consider duration t equal to 35 to t equal to 40 seconds. In this interval, what is area under AT diagram? No area, 0 area. This is area under AT diagram, which is 0 in this case. That is equal to velocity at t equal to 40 seconds minus velocity at t equal to 35 seconds. So put that value t equal to 35 seconds and you will get velocity at t equal to 40 seconds also 13.875 meters per second. Of course, acceleration is 0, so no change in velocity in this time interval. So check velocity at t equal to 35 13.875 meters per second, and velocity at t equal to 40 seconds is also 13.875 meters per second. Now we have found out velocities at all these important instants. Now we are ready to draw VT diagram. How to draw VT diagram? Try to understand. Focus on all velocity values only. Along x-axis, time in seconds. Along y-axis, velocity in meters per second. Okay. Now, you are going to plot all these points. But first, take care of proportions and mark all these important instants here. Check here, 0 to 10, it must be same as 10 to 20 because this base is 10, this base is 10. And 20 to 35, this base is 15. So it must be greater than 10. So when you mark these points, take care of proportions. So mark all these points or instants 10, 20, 35 and 40 along x-axis in VT graph also. Check here, I have marked all these points here. Then mark all these velocity values along y-axis. Now listen to me very carefully. You are going to draw freehand sketch. To get correct shape of the curve, you should mark these points by taking care of proportion. Doesn't mean that you should draw to the scale diagram. It's little time consuming. So don't draw to the scale diagram unless it is asked to draw. Okay, but it's not necessary to draw to the scale diagram, but take care of proportion. In the sense, if you mark 4 meters per second somewhere at this level, watch here, then 8 meters per second, it must be double of that. It's better to draw or to mark highest value of velocity first. This is highest value of velocity. That means VT diagram will not go above this level. Okay. And with reference to this value, with proportion, in proportion with this value, you should mark all other values. So now we'll mark all other points. Watch here. T equal to 4. It is slightly less than 1/3. So approximately check 1/3 of this 13.85 and slightly below that you mark 4. Then 12. 12. It is 3 times 4. So here somewhere it will be 8 and here somewhere it will be 12. So mark that. So this is how we have marked all these points. So you need not mark these points to the scale, but take care of proportion, otherwise you will not able to complete the curve. Now at t equal to 0, velocity is 0. At t equal to 0, velocity is 0. I have marked this point. This is the point, one of the points on the curve, on the VT diagram. Now at t equal to 10, v is 4 meters per second. So this is one of the points on the curve. Now at t equal to 20, velocity is 12 meters per second. So this is one more point on the curve. Now at t equal to 35, velocity is 13.875. So this is one of the points on the curve. And at t equal to 40 also, velocity 13.875. So this is one of the point on the curve. This is how we have plotted all these points. Now we should join these points. So how to join these points, try to understand. Everything is important. How to mark these instants, how to take care of proportions, and how to join these points. Now listen. AT diagram is given. That is why I am asking you this question now. How AT diagram is related with velocity? Now since we are drawing VT diagram, I am asking you how VT diagram is related with acceleration. Slope of VT diagram is acceleration. Therefore, when you draw VT diagram, your focus must be on AT diagram. Now how we should use AT diagram? To draw VT diagram, try to understand. To identify shape of curves in this VT diagram, how to use AT diagram, that is what I am telling you. So from t equal to 0 to t equal to 10 seconds, acceleration is increasing. What does that mean? Slope of VT diagram is increasing. Listen to me very carefully. Acceleration is slope of VT diagram. How we use this information to draw VT diagram? Listen. Here acceleration is 0. That means here slope of VT diagram is 0. Now 0 slope means horizontal line, of course. So when you start drawing VT diagram at origin here, it should be a horizontal line. Initially it should start as a horizontal line. Acceleration is increasing here. Y coordinates check in AT diagram. Here acceleration is increasing. So in VT diagram, slope must increase. Acceleration is slope of VT diagram. So when you join these points, you should join as a curve with increasing slope. So check here, slope you can identify by tangent to the curve. Or imagine you are walking along a road that has this curvature. So from left, you start walking on the road. To the right, you will find that slope is increasing. Correct? So this is that increasing slope curve. So now I'll use these words: increasing slope curve, decreasing slope curve. This is increasing slope curve. Okay. Now from t equal to 10 to t equal to 20 seconds, acceleration is constant and acceleration is slope of VT diagram. So acceleration is constant in the sense slope of VT diagram is constant. So it must be a straight line. So draw a straight line. Now there is sudden drop in acceleration. So what does that mean here? There is sudden, this is very important. Many students they don't know this. Sudden change in acceleration. That means here at t equal to 20, there must be sudden change in slope. Now sudden change in slope means it must be corner here, sharp corner. So when you draw the curve or when you proceed, the curve must not be tangent to this line. There must be sharp corner here. In this case, at t equal to 10 seconds, try to understand, this is very important. At t equal to 10 seconds, what is acceleration? So your answer is 0.8. From t equal to 10, if you check, acceleration is 0.8. At t equal to 10 seconds, what is acceleration? 0.8. Now I am asking you, at t equal to 20 seconds, what is acceleration? Now you cannot say 0.8 only, because you can check here, there are two values of acceleration. Which are the two values? 0.8 and 0.25. In fact, acceleration suddenly drops from 0.8 to 0.25. So here also slope suddenly drops and you get a sharp corner here. If this inclined line has certain slope, so here suddenly that slope must reduce, so automatically you will get sharp corner. So have you realized how we use this logic of acceleration is slope of VT diagram? Acceleration at particular time instant, if acceleration suddenly drops, so you get two values or vertical straight line in AT diagram, then it means there is sharp corner in VT diagram. So that is why at t equal to 10, these two curves, that is initial curvature and this straight line, they must meet tangentially. But at t equal to 20, this is not tangential joint, there must be sharp corner. So this is what I explained you. Now further, from t equal to 20 seconds to t equal to 35 seconds, is it a straight line? No. When you draw a straight line in VT diagram, when acceleration is constant. Acceleration constant means slope of VT diagram is constant. But from t equal to 20 to t equal to 35 seconds, acceleration is reducing. Acceleration means in AT diagram, check y coordinates. From 20 to 35, y coordinate for the line are reducing. That means acceleration is reducing. So acceleration is reducing, it means slope of VT diagram must reduce. That is one thing. So you are going to draw a reducing slope curve. This is increasing slope curve from 0 to 10. But here we are going to draw a reducing slope curve. And not only that, what is acceleration at t equal to 35? 0. That means slope here at t equal to 35 must become 0. So when you draw VT diagram, here slope of VT diagram must be 0. That means VT diagram must turn to horizontal here. Check here. It is not a straight line. Also check here. This is not tangential joint here. And here that curve has become horizontal. This curve has certain slope here but reduces. Slope reduces and it becomes 0 here. So this is correct shape of VT diagram from 20 to 35. And 35 to 40 acceleration is 0. So VT diagram is horizontal line. So this is how we have completed VT diagram. Listen to this part of the lecture once again so that you will understand how to identify shape of the curves. If you made mistake in drawing shapes of these curves, then it's no use of doing all these calculations here. But once you understand, in no time you will able to identify this shape. Acceleration is increasing, slope is increasing here. Acceleration constant, it is a slope constant. Acceleration reducing, so slope reducing. You automatically get sharp corner. If there is sudden drop in acceleration or sudden rise in acceleration, you will not able to draw tangential curve. Here you will get sharp corner automatically. Only thing is, I explained to you that unless you mark all these points by taking care of proportion, you will not able to draw this correct shape. After completing VT diagram, you should name these curves. So this curve from 0 to 10 is parabola. From 10 to 20 seconds, it is straight line. From 20 to 35 seconds, it is a parabola. And 35 to 40, it is horizontal line. If you don't label this portion as horizontal line, one may think that it is continuation of this parabola. But this portion of the curve is not a parabola, it's horizontal line. How come this curve parabola? I'll explain you little later. But right now remember, you will have to label these curves. Now you are also asked to draw position time diagram. So tell me how AT diagram is related with position. So moment of area under AT diagram from t equal to t1 to t equal to t2, and this moment is about t equal to t2. Now what is that, you will understand now. Plus initial velocity, initial means in this interval initial, into t2 minus t1, that gives you change in position. To draw xt diagram, you are going to find position values at all these important instants. At t equal to 0, x is 0, that is mentioned in the problem already. Particle starts at origin. What does that mean? Its initial position is 0. So select interval, the time at which position is known and the time at which position to be found out. So we want to know position at t equal to 10 seconds at this stage. Of course, we are going to find position of all these important instants one by one. Time at which position is known and time at which position to be found out. So now how to write this bracket, that is very important, try to understand. Moment of area under AT graph from T1 to T2 about T2. This triangular area is area under AT graph from t equal to 0 to t equal to 10 seconds. But we don't just want area, we want moment of area. So moment of area is area into distance of its center or centroid. So this is centroid, area into distance of its centroid, that is moment of area. In this interval, what is a T2? T2 is 10 seconds, T1 is 0 and T2 is 10 seconds. So this is moment of area from t equal to 0 to t equal to 10 seconds about t equal to 10 seconds. So here it is t equal to 10 seconds. Now t equal to 10 seconds, that means it is vertical line. So t equal to 10 seconds is this vertical line. So it is moment of this area about this vertical line. Means area into distance of its centroid from t equal to 10 seconds, this vertical line. Location of centroid of a right angle triangle. From its vertical edge, 1/3 of its base. From vertical edge, 1/3 of its base. So 1/3 of 10. So this is that distance. So this is moment of area under AT graph from 0 to 10. So from 0 to 10, area is base is 10, height is 0.8 divided by 2 into distance of its centroid from t equal to 10 seconds. Okay. Plus initial velocity into duration. Now initial velocity means not when motion starts, initial means in this duration initial, that means at t equal to 0. But at t equal to 0, velocity is 0. So this part, v initial velocity into duration will become 0 in this case. And that is equal to x at t equal to 10 seconds minus x at t equal to 0. We are simply using this formula. And x at t equal to 0 is 0. So put it here and you will get x at t equal to 10 seconds as 13.33 meters. Now next duration, 10 to 20 seconds. Moment of area, that is what you should understand. Moment of area is this area into distance of its center. Now it is rectangular area. What is base of the area? 10. And you know location of centroid of a rectangle, h by 2, b by 2. Now we want distance from t equal to t2, in the sense from t equal to 20 seconds. So from t equal to 20 seconds, distance of this centroid is half of its base, and that is 5. Base is 10, so half of base is 5. So now moment of area, 10 into 0.8 into distance of its centroid from t equal to 20, that is 5, plus initial velocity. Now initial means not t at t equal to 0, initial means in this interval initial. So in this interval, initial means at t equal to 10 seconds. So what is velocity at t equal to 10 seconds? If you remember, we have already found out. So check, in earlier VT diagram, we have already shown that velocity at t equal to 10, that is equal to change in position, x at t equal to 20 seconds minus x at t equal to 10 seconds. Now x at t equal to 10 seconds is 13.33, put it here, and you have found out value of x at t equal to 20 seconds. So this is a position at t equal to 20 seconds. Now consider duration from t equal to 20 seconds to t equal to 35 seconds. Now in this duration, 20 to 35 seconds, this is that triangular area. So moment of this triangular area, its distance of its centroid from t equal to 35 seconds. That's important. We know position of centroid of a right angle triangle, h by 3, b by 3. So from its vertical edge, distance is 1/3 of the base. Now how much is that base here? 20 to 35, that means 15. So 1/3 of 15 from vertical edge of the right angle triangle. So 1/3 of 15, that is 5. 5 is the distance from that vertical edge of the triangle, but we want its distance from t equal to 35, and that is 10 cm. So write properly moment, area into distance of its centroid, that is 10, plus initial velocity, initial in the sense at t equal to 20 seconds. In this interval, initial is t equal to 20 seconds. So at t equal to 20 seconds, the velocity is 12. So that is initial velocity into t2 minus t1, 35 minus 20, into t2 minus t1, that is 35 minus 20. That is equal to x at t equal to 35 seconds minus x at t equal to 20. Now put value of x at t equal to 20 here, and you will get x at t equal to 35 seconds as 292.08 meters. And interval 35 to 40. from t equal to 35 seconds to t equal to 40 seconds. What is moment of area? 0, because area is 0. From 35 to 40 seconds, there is no area under this curve. So area is 0, so moment of area is 0, plus initial velocity. Now in this interval, initial means at t equal to 35 seconds. So at t equal to 35 seconds, velocity we know already, 13.875 into t2 minus t1, so 40 minus 35, and that gives you x at t equal to 40 minus x at t equal to 35 seconds. Put value of x at t equal to 35 seconds here, and you will get x at t equal to 40 seconds as 361.45 meters. So this is how we have found out values of positions at this important time instance. So we are ready to draw xt diagram now. Now focus on all values of x at this important instance and plot these points by choosing x, that is position on y-axis, and time t on x-axis. So along x-axis time, along y-axis position. Now mark these important instance along time axis. Take care of proportions when you mark these instance. And now position values. First, highest value of position 361 seconds. Now with reference to 361, this value of position, you mark other values of position. So 93, this is 300. So 1/3 of 300, it is 100. So less than 1/3 of this distance. I have marked 93.33. Then 13.33. So 93 about 100 and 13.33 nearly 10. So it is 1/10 approximately. So this is how we should take care of proportion, so that we'll able to draw proper curve. Then 292. So this is how I marked at this point also. And at t equal to 0 x 0, we already know that point. So let's plot all these points carefully. So at t equal to 0 x 0, at t equal to 10 x is 13.33, at t equal to 20 x is 93.33, at t equal to 35 x is 292.08, and at t equal to 40 x is 361.45. Now all these points you are going to join by curves. So how to decide shape of those curves? So listen, velocity is slope of xt diagram. So you should refer vt diagram, not acceleration time diagram. Now refer vt diagram and then identify shapes here in xt diagram. Now watch here, what logic you are going to use? Velocity, slope of xt diagram. We have already drawn vt diagram, refer that. So don't get involved in shape of vt diagram. Listen to me very carefully. Don't get involved in shape of vt diagram. Just tell me from 0 to 10 whether velocity is increasing. That is y coordinate in this diagram, because velocity is along y axis. 0 to 10, tell me whether y coordinates are increasing. Yes. So that means slope of xt diagram is increasing. So draw shape that suggests you increasing slope. So here it is increasing slope curve. 0 to 10, it is increasing slope curve. Now 10 to 20, whether velocity is increasing? Yes. From t equal to 10 to t equal to 20, velocity is increasing. So again, from t equal to 10 to t equal to 20, you should draw increasing slope curve. So this is again a curve that suggests you increasing slope. Now 20 to 35, tell me whether velocity is increasing. Why I am asking you whether velocity is increasing? Because velocity is a slope of xt curve. So yes, velocity is increasing again. Just check whether velocity is increasing from 20 to 35. So yes, At t equal to 20, velocity is 12. At t equal to 35, velocity is 13.875. So velocity is again increasing. So we should draw increasing slope curve. So this is that. This is not straight line. It is a curve, increasing slope curve throughout up to t equal to 35. Actually, these are three different curves which are meeting tangentially here. You should not get sharp corners here at this. Sharp corner here means sudden change in slope of the curve. Sudden change in slope of the curve means here sudden change in velocity. Is there anywhere sudden change in velocity, that is vertical line in VT diagram? No. So there must not be sharp corners here. And from 35 to 40 seconds, velocity constant means the slope of xt diagram is constant. So from 35 to 40, it is straight line. It is straight inclined line. Constant slope in the sense it is straight inclined line. So this is how we have completed xt diagram. Now label these curves. So cubic curve, when it is a parabola, here it is cubic curve. When it is a straight line, here it is a parabola. So again, when it is a parabola in VT diagram, it is cubic curve, that is third degree curve, and horizontal line in VT diagram, that is straight line here. Now this curve is parabola, this curve is cubic curve. How we identify that? That is what I am going to tell you. Note down this table somewhere. Now try to understand how to identify shape of the curves. AT curve is 0 in the sense, for example here 35 to 40, acceleration is 0. So when acceleration is 0, in AT curve we get acceleration 0, then VT curve is horizontal line, 35 to 40, check VT diagram is horizontal line. What does that mean? When acceleration is 0, velocity is constant. When acceleration is 0, velocity is constant. Is anything new in this? No. And when velocity is constant, xt curve is inclined line. Acceleration 0, velocity constant, and x is equal to v into t plus x0. These are standard equations of motion mentioned here as a curve. So diagrammatical representation of these three equations: acceleration 0, velocity constant, x is equal to v into t plus x0. When AT diagram, acceleration time diagram, is horizontal line, for example 10 to 20 seconds, it is horizontal line. Acceleration is constant. When acceleration is constant, v is equal to u plus at. The equation is like y equal to mx plus c. So it is inclined straight line. When acceleration is constant, v, velocity, v is equal to u plus at. It's like y is equal to mx plus c. That is why. So these are the same equations of motion. Acceleration constant, v is equal to u plus at, and here x is equal to ut plus half at squared. At squared, t squared. So it is a parabola. So acceleration constant, v is equal to u plus at, and x is equal to ut plus half at squared plus x0. The same three equations in terms of corresponding curves I have mentioned. Similarly, when acceleration time diagram is inclined line, for example 0 to 10 seconds, it is inclined line. So here it is parabola, 0 to 10, it is parabola, it is cubic curve. For example, if acceleration is equal to kt, k is constant, if acceleration is equal to kt, then integrating acceleration you get velocity. So v is equal to kt squared by 2. So it is a parabola because it is function of t squared, and velocity is function of t squared. When you integrate velocity, you will get x is equal to t cube by 3. So again power of t increases. So when it is x, it is cubic equation. That is why we say cubic curve. Now important thing is quickly to write name of these curves here in the diagram. Remember this table, and simple: 0 horizontal line, inclined line, horizontal line, inclined line, parabola, and inclined line, parabola, cubic curve. So now take a pause, note down this table, remember this table. check sharp corner. VT diagram. Sharp corner in VT diagram means sudden change in slope. So when there is vertical straight line in AT diagram, you should get sharp corner in a VT diagram. Here there is no sharp corner because there is no vertical straight line in AT diagram. Remember, sharp corner in VT diagram, that suggests you sudden change in slope, and acceleration is slope of VT diagram. So remember those 5 points to remember I have given you initially, and knowing those points you will able to draw AT, VT, XT diagrams easily. Of course, little practice is required. Read all those solved problems I have given you and you will understand it better. Thank you.